Saxon's Calculus, Lesson 91, is about limits and continuity and then differentiability. So in Section A, they are basically doing a long explanation to remind you that you do not have a limit if you do not have continuity or the line continuing in all directions. So if there is a gap, then at that gap, there cannot be a limit. And they show a picture at the bottom of 444, which I chose not to draw because it was relatively complex. But if you were looking at that graph in your book, it says it's not obvious, but for a function to have a derivative at point C, it is necessary that that function be continuous at point C. And in that diagram, you can see that it is not. It's discontinuous. And then on page 445, they go through trying to prove to you why continuity is important by going through that basic formula f of x minus f of c over top of the x minus c, and then using the limit of x approaching the c, and then they work that through, and then their conclusion is that when you have a limit of x approaching c and you're plugging that into an f's equation, the limit will be the answer you get when you plug in c, but you already knew that. And so then their conclusion is the existence of a derivative at c tells us that the function has to be continuous at c. So if there is a limit, it means it is continuous. Okay, now part B is differentiability. And so they remind us that when we have a graph and it has a sharp point, that we are not differentiable at that spot, and we call that then a singular number. Now, in example 1, they say, use a left hand and a right hand derivative to determine if this given function with the absolute value of x minus 2 will be differentiable at 2. Now you can see in the graph, or if you remember, that when you're dealing with an absolute value, you're getting a V graph of some sort. Now I didn't put that in the right spot, but well, actually I didn't do too badly. But what we're testing is from the right hand and from the left hand. And so in the swoop here, we know that's the positive version, so it's going to be the x minus 2, and that's happening where x is greater than 2. And then the reverse of it will be the negative x plus 2, and that's occurring when x is less than the 2. Well, those are technically or equal to, because they share the same value at 2. So we know that 2 would technically then be called a singular number, because it's not differentiable right there. But that's not what this was asking about. So what you want to do is derive each of these and see if you come to the same conclusion. If you do, then yes, it is differentiable at 2. Well, plug in the 2 after you derive. If it's not, then it is not. Okay, so when we derive this one, we basically get the 2 is dropping off x, so that goes to 1. Yes, sorry, I had to think my way through that. And then if we differentiate this one, we get negative 1. Now, technically, you can't plug 2 into those, so I'm just looking at the numbers 1 and negative 1, and since they're not the same, it does not have a derivative at point 2, which I said it wouldn't because that was the vertex point. Okay, now, example 2. For what values of x in the piecewise function shown at the top of the next page will be differentiable? Okay, so I'm going to pause it while I graph that. Okay, so this is what they had given me, where f of x is x squared, and I didn't write it, but it's stating when it is above or equal to 1, and it is 2x minus 1 when it is below the 1. Now, in my curve, this is a little more exaggerated, but the idea is that if I plug in 1, obviously 1 squared is 1, so that's the start of that one because it said 1 or above. If I plug in 2, I get like 4, so I knew it was way up there. And then if I plug in the 1 here, that's 2 minus 1 is 1. However, so it's continuous. I'm not putting a gap. It is the same dot, but that one was not or equal to 1, so it didn't really matter. And then I plugged in 0, so that gave me -1, and then I'm swooping down here the further I go. So since we are using the left and the right hand derivatives, we are going to derive our x squared to 2x, and our 2x minus 1 goes to 2. Well, what do we get when we plug in, because it says for what values is it differentiable? Okay, yeah. So since 2 has to be the number for them to be differentiable, they have to be the same. What number would I use for x to turn it into 2? Well, x would have to be 1 to make it differentiable there. Now, the conclusion that I need to draw is not just about the value for 1, because even though it's said for what values is the piecewise function shown differentiable, and we have shown that we do get the same answer of 2, they're clarifying that this will work for all real values. Now, how do they come to that conclusion? Because this one, for everything less than the 1, is always the 2. That's a set answer. For any number then that is going above the 1, I have an answer that's working, even though the numbers may be changing. It's continuous. There is no gap at the 1, and since that is no, I'm losing a piece. I am trying to focus on the fact that these both got to 2, which meant that my right and my left hand testing of the limit was correct. Then it is going to work for all real values. Now, example 3. Let f be defined as the following. F of x equals the absolute value of x plus 3 and ax squared plus bx, and this is for when I am less than 1, and this is for when I'm greater than or equal to 1. Find the values of a and b so that the function will be continuous and it will be differentiable at x equals 1. So let's graph this so we can see what we're dealing with. For things that are less than 1, 1 plus 3 is 4. So 1, 2, 3, 4. And I want to put a dot there, but I don't think no, it's not or equal to. So this has to be an open circle. And then I'm going less than 1, so 0 would give me 3. -1, because it's an absolute value, goes to 1, plus 3 is 4. So this is the little piece of the v. It just doesn't continue that way. And then at 1 itself, I don't have an equation, but I know it's an x squared, so it's some sort of parabola. And as long as I have a colored in dot that fits into this hole, wherever it may be, and the parabola, I would be okay. Obviously, if it's down here, it's not being continuous. Okay. So if I then look at the left and right hand limits, the left one, if I'm coming here and swooping up, then 4 is its limit where it stops. Now in this equation, the limit is going to be a plus b. It's whatever the combination of those two are, and we've worked through that in an earlier lesson. I know that the two limits, in order for this to be continuous, have to be equal to each other. So the 4 has to equal a plus b. That's still not enough for me to solve for a and b separately. So let's try deriving and see what we get. So the derivative of our x plus 3 drops off, so we just get a 1. The derivative on the other side goes to 2ax plus b. And then we plug in the fact that it's 1, so that's going to give me 2a plus b, basically. And now I have those two equations. 4 equals a plus b, and 2a plus b has to equal the 1. And I need to solve. So let's work through, I could substitute or eliminate. Let's eliminate the b's. So I'm going to write these kind of together. 1 equals 2a plus b. So if I subtract these, that gives me 4 minus 1 is 3. 1 minus 2 is negative 1a, and b minus b is gone. So a will be negative 3, then plug that back in, and 4 equals negative 3 plus b, so b has to be 7. Now we have all the parts. Our equation would be y equals negative 3 with our x squared plus our 7x. And if that is the line or the parabola actual